Okay, so in this video we're going to be talking about some different forces that you should know and how to draw free body diagrams. In the last video we talked about Newton's first law, which is a conceptual law, and just to remind you what Newton's first law says, Newton's first law says that an object at rest remains at rest, and an object in motion remains in motion at constant velocity unless acted upon by a net force. Okay, and so we talked about what a net force is in the last video. Remember, the net force on an object is basically what you get when you take all the forces on an object and you add them all up, taking into account direction. Okay, and so in this video we're going to get into more specific forces, and then we're going to learn how to draw free body diagrams. And basically, in order to correctly draw a free body diagram, you have to, number one, know some different types of forces, and number two, you have to understand Newton's first law. Okay, so here are the most common forces that you're going to see on the assignments. Okay, so first things first, what we call weight, the force of gravity. Okay, the force of attraction between two objects. Again, we also call that weight. We write Fg for the force of gravity. Just as a hint, all objects near the surface of a planet experience a downward force of gravity. And so that means when we're drawing free body diagrams in a few minutes, as long as it's not in space, as long as the object is close to the surface of the planet, it automatically is going to have a downward force of gravity. Okay, so later when you're drawing free body diagrams, and you're wondering like, oh, how do I know what forces to draw? Look at this slide and look at the next slide. Okay, because they give you really important information that you need to know to answer the free body diagram questions. Okay, so all objects near the surface of a planet experience a downward force of gravity. Okay, you also have a force called tension. Now for tension we write Ft. Tension is a force you have anytime you have a string or a rope. Okay, objects touching a rope or string will experience a force of tension along the rope in the direction that the rope is pulling. Okay, so for example, let's say you're, I don't know, let's say you hang an object from a string and it's, hanging from the ceiling. Tension would be the force in the string keeping the object from falling. Or if you think of, like dragging a sled when you go sledding when it's cold outside, usually you drag it with a rope. Okay, in that case, tension is the force that's acting on the sled to pull it. Okay, so anytime you have a rope or a string, you're going to have tension in the direction that the rope is pulling. Okay, now we also have friction. Friction is a very common force to see. Okay, friction is always a force that opposes motion. And basically what that means is if an object is moving to the right, the force of friction would be acting to the left. If an object is moving to the left, force of friction would be acting to the right. Okay, so friction always opposes motion. Okay, now a context clue you can tell, or you can use to know if you have friction in a given problem is the term rough surface. So anytime you're dealing with a rough surface, you can assume that surface has friction. Now do keep in mind that you only have friction when you have an object touching a surface. So an object falling through the air is not going to have friction, but an object sliding on the ground or sliding on the wall can have friction acting in the opposite direction of motion. Now, the fourth force that's really common to see is what's called the normal force. Now, for some reason, people confuse normal force and net force, and they are not the same thing. Okay, for normal force, we write Fn. And I guess because Fnet and Fn, like both have the letter N, people get confused. Fn is not the same as net force. Okay, the net force is what you get when you add up all the forces. We talked about that in the last video. That's really important for like Newton's first law and Newton's second law. Fn is what's called the normal force. Now, you don't really need to know that what I'm about to say, but the word normal basically means perpendicular. Okay, hopefully you know what perpendicular means from like geometry. Okay, so you have a normal force anytime you have a surface and something is pushing on the surface. Okay, and the normal force always acts at a 90-degree angle to the surface. So, for example, let's say I'm going to erase a little bit of this, and excuse my really bad drawings. I apologize for that. But let's say you're standing by a wall, and here's you, and let's say you push on the wall. Okay, now you apply force to the wall. I would call that an applied force. I would call that FA for applied force. However, the wall also pushes back on you. That's why your hand doesn't go through the wall. Okay, so if you push against the ground or you push against the wall, okay, you feel that surface pushing you back. Okay, the force pushing you back from the wall or from the ground, that's what's called the normal force, and it always acts at a 90-degree angle to the surface. So in this case, the normal force would be coming out from the wall, and we would call that Fn. Okay, not net force, normal force. Okay, normal meaning perpendicular. Now the net force is what you would get when you add these two forces up, and it would be 0 in this case because the wall is not going to move, of course, when you push it. And so you have a normal force anytime an object is touching a surface. And finally, applied force. Applied force is just like a generic term for anything that's pushing or pulling on an object. So, for example, I push on the wall, I call my force the applied force just because I'm applying a force. Okay, now pause it here and make sure you add all the information here into your notes because this is how you're going to tell what forces are given in different situations. Okay, it's really important that you know that. Okay, so let's go to the next slide. Okay, what we're going to do now is we're going to draw FBDs. FBD stands for free body diagram. And basically, a free body diagram is a diagram that shows all of the forces acting on an object. Now, it's really important, two things. Number one, a free body diagram has nothing to do with which way an object is moving. Okay, a free body diagram does not tell you which way an object is moving. All it does is tell you the forces acting on an object and which way those forces are acting. Okay, second of all, the lengths of the arrows are important because the length of the arrow has to do with the size of the force. And we saw when we looked at the simulation in the last video, okay, that if you have two forces going in opposite directions, if they're the same size, the net force is going to be 0 because those two forces are going to cancel each other out. Okay, if one force is bigger than the other force, you need to indicate that by drawing one arrow longer than the other arrow. Okay, so the length of the arrow is important. So here's how we're going to do this. Step 1, you draw a box or a dot to represent the object. Okay, I'm going to draw a dot because that's how I like to draw my FBDs. You can draw a box if you want. Okay, and the reason you draw a box or a dot is just so you don't spend a lot of time drawing the actual picture because that's not important from a physics perspective. Okay, so draw a dot or a box to represent the object. Step 2, and this is what a lot of people have trouble with. Determine which force or forces are acting on the object based on the context of the situation. What I mean by that is these forces right here, you need to make a list of which of these forces apply to your object based off of the situation. Okay, and you do that using context clues, and we'll do lots of examples so you know what I mean. Okay, but it's really important that you understand how all these forces come about. Step 3. Draw arrows representing the forces going away from the box or away from the dot, making sure to draw the length of the arrow appropriately. Okay, arrows should always be drawn away from the dot, not towards it. Okay, and step 4, correctly label the forces using subscripts. Okay, so these are the steps drawing free body diagrams. I'm going to do plenty of examples in this video, and then I'm going to do the first 2 problems on your practice worksheet just to give you an idea of what these should look like. Okay, so example 1. It says a book is at rest on a tabletop. Diagram the forces acting on the book. Now, the first thing I'm going to do is I'm going to label which forces are acting on this object. Now, how do I know that? Well, I go back to my list of forces that I talked about before, and I run through that list, and I see which of them make sense in this context. Okay, so first things first, force of gravity. I said before that unless the object is in space, right, you always have a downward force of gravity. So I'm going to have force of gravity. Okay, I run through my list. Force of tension. You only have force or tension if there's a rope or a string. There's nothing in this problem that indicates a rope or a string, so I don't have tension. Okay, force of friction. Okay, there's no force of friction, and the reason there's no force of friction is because the object is not trying to move. The book is just sitting on the table, and friction always opposes motion. Okay, so if you push on the book and it doesn't move, then you might have friction. Okay, but because the book is not trying to move, there's no friction. However, there is a surface. This tabletop is a surface, and that means there has to be a normal force. Okay, and there's no applied force because the book is not being pushed. So this is what my FBD should look like. Okay, I draw a dot to represent the object. Oh, and one more thing. How do you know how long to draw the arrows? Well, the length is really important, but what is important is that the lengths are correct relative to each other. This right here is crucial to drawing the FBD correctly. The book is at rest. Okay, you need to understand Newton's first law to draw these FBDs correctly. Remember, an object at rest remains at rest if, and only if, the net force is what? 0. Okay, so the fact that the book is not moving tells me that net force must be 0. Now, how does that help me draw my free body diagram? Well, if I have two forces and they have to add to be 0, that means that they should have the same length. Okay, so I'm going to draw force of gravity going down. Gravity always goes down. Okay, and I'm going to draw the normal force, same length, going up. Okay, just like that. And that's my answer. That is my free body diagram for this situation. Now, do they have to be super perfect? No, but if you mean for them to be the same length and you're not good at drawing, you might want to write a note off to the side, something like, same length. Okay, because if they are not the same length and you don't make a note and it's not pretty close and I can't tell, then I'm going to count points off. Okay, the length is important. The net force must be 0 in this situation because the book's not moving and it's at rest. Okay. So if that's not clear from your FBD because you can't draw, like I'm not good at drawing either, then let me know that they should be the same length. Okay, so pause it there if you need to look at that. Okay, so example 2. It says an egg is free falling from a nest in a tree. Neglect air resistance. Draw a free body diagram showing the forces involved. Okay, so a couple things. Number one, the word free fall is a vocab word, and we've talked about free fall before. By definition, an object in free fall, the only thing affecting it is the force of gravity. Okay, so right off the bat, if you know that, then this is a very easy question. Now, if you don't know that, then you have to run through your checklist and think what forces are acting on the egg. Okay, so we have force of gravity because we're not in space. Then we go to tension. Do we have tension? Is there a rope or string acting on the egg? No. Okay, do we have friction? Well, the egg's not touching a surface, so probably not. There's no air resistance because, it says neglect air resistance, so that's a context clue. Do we have a normal force? Remember, you only have a normal force if you have a surface, and we don't have a surface because the egg is like falling in the air. Okay, it's not touching a surface, and there's no applied force because nobody's pushing or pulling on the egg. So that means the only force is the force of gravity. So my FBD, my free body diagram, should just look like this. A dot to represent the egg, force of gravity arrow going down, boom, I'm done. Okay, easiest free body diagram you could have. Okay, pause it there if you need to look at that. Okay, example 3. This one is kind of interesting, and this one is actually going to involve a force we haven't talked about. It says a flying squirrel is gliding from a tree to the ground at constant velocity. Consider air resistance. Okay, right off the bat, that means we cannot ignore air resistance. In fact, they're probably telling us, hey, there's going to be air resistance. Now, at this point, you should be saying, wait, air resistance, that's not one of the forces you talked about before, and you would be correct. Okay, so watch what I'm going to do. I definitely have force of gravity acting on the squirrel, and then I'm just going to write F, and I'm just going to put air, F air, okay, for air resistance. Now, the forces we talked about before, that's not every force in existence. That's just the most common forces. If there's a force that you don't know what it could be, like air resistance or a force from a rocket or a force from like a car engine, then just, use subscripts creatively. Like if there's a force from your car engine, there's nothing wrong with putting F engine. You could also put F applied. Okay, in this case, I'm going to put F air. Now, I draw a dot to represent the flying squirrel. Okay, by the way, if you don't know what a flying squirrel is, go on YouTube and look up flying squirrel. It's pretty cool. I draw my free body diagram. I have the force of gravity going down. Okay, how do I know gravity is going down? Because the force of gravity goes down. That's like common sense. And then you might say, how do you know how to draw the air resistance force? Okay, this right here, constant velocity. Think back to Newton's first law. Okay, an object at rest remains at rest, or an object in motion remains in motion at constant velocity if there is no net force. This is a context clue. Okay, this is telling us, hey, the net force on this object is 0. Okay, because the object is in motion, but it's in motion at constant velocity, therefore the net force must be 0. How does that help us draw the FBD? If I have a force going down and I know, the net force has to be 0, that means the air resistance has to be the same length going up. Okay, just like this, F air. That's my FBD for problem 3. Okay, pause it there if you need to look at that. Okay. Example 4. A rightward force is applied to a book at rest. Okay, so this is going to be an applied force. To move it across the desk, consider frictional forces. Look for those context clues. Consider frictional forces. Rough surface. They're telling us in the problem there's going to be friction. Neglect air resistance. Construct a free body diagram for the book. So we have FF. We have FA, just from reading the problem. We have force of gravity because we're not in space. And guess what? Do we have a surface? Yes. That means we have normal force, Fn. Do we have tension? Well, no, because there's not a rope or a string. Okay, so I'm going to draw this for FBD. Now, the object is going to move. It starts off not moving, but it is going to move. It's a slightly ambiguous question because it doesn't say if it's moving at constant velocity or not, but since it doesn't say that, I don't think we can assume it is. So watch what I'm going to do. I have the force of gravity going down. How do I know that? Because gravity goes down. The normal force, remember, always acts at a 90-degree angle to the surface, so the normal force is going to go up, and the normal force is going to balance out the force of gravity. Okay, the reason I know that is because the book is being pushed to the right. The book is not going to fall down to the ground. It's not going to fly up into the air. So those two forces going up and down have to balance each other out. There's a force that is applied to the right. So I'm going to draw an arrow to the right, label that FA for applied force. And there is also a force of friction. Remember, friction always acts in the opposite direction of motion. So if I'm pushing it to the right, that means the force of friction must be to the left. Now, because I don't know for sure if it's, constant velocity or not, I'm going to assume it's not. Watch how I draw this FBD. I'm going to draw the force of friction shorter than the applied force. So when you add up all these forces to get the net force, guess what? It's not going to be 0. These two forces cancel out. FA is bigger than FF, and so when you add those two together, FA wins because it's longer. That means the net force is not 0. In fact, the net force is to the right. And what does that mean? The F net is to the right. What does it mean if you have a net force? Well, going back to Newton's first law, if you have a net force that's not equal to 0, that means the object is going to accelerate. So what I would say is this object is going to accelerate to the right. Well, accelerate to the right. Okay, now it just says to draw the FBD, so you wouldn't necessarily have to put that, but I'm just telling you this object is going to accelerate to the right. What if I had drawn these two arrows the same length? Then that would mean the object is moving at a constant velocity. So whether it's moving at constant velocity or whether it's accelerating just has to do with how long the arrows are relative to each other. Okay, so make sure you draw the arrows correctly. A couple more examples. Pause it here if you need to look at that. Okay. Let's see. I'm just going to do one more on here, and then I'm going to do 2 from your worksheet really quickly. Okay. A man drags a sled across loosely packed snow with a rightward acceleration. Draw a free body diagram of the forces acting on the sled. Okay, loosely packed snow If the snow is not super smooth, it's probably going to produce a little bit of friction. Okay, now it says a man is dragging a sled. In my mind, when I think of dragging a sled, I think of like attaching a rope to a sled. And so I think if there's a rope or string, there's got to be a force of tension. Okay, and of course, there's got to be force of gravity. And there's also going to be a normal force because guess what? He's dragging it across the surface. Anytime you have a surface, you automatically have a normal force. So here's what my FBD is going to look like. Force of gravity going down. Normal force going up to balance out the force of gravity because it's not going to fall through the ground. By the way, these two should be drawn the same length. Okay. Now it says the acceleration is to the right. That means the net force is to the right. That means we have Ft to the right and force of friction to the left, but the force of friction error is going to be smaller because the net force is to the right. Now, what if it said a man drags a sled to the right at a constant velocity? Well, if it's moving at a constant velocity, it doesn't matter if it's moving left, right, up, or down. If it's moving at a constant velocity, the net force must be 0, and then all of the forces would have to balance out. Okay, so pause it here if you need to. And then just to give you a start, I'm going to just kind of draw the answers on here so you can check your work. These are the first two problems on your practice worksheet. Okay, so maybe try these on your own before you take a look at this. And I'm just going to do it really quick. Just so you can see the answers. Okay. Notice, by the way, because it's a constant velocity, the net force must be 0. So I would write F net equals 0 because it says be sure to include whether the net force is 0 or not 0. This one, there's a rocket. I don't even know what you would call that force. So guess what? I'm just going to call it F rocket. Okay. It's on ice, so that probably means there's no friction. Anytime it says smooth surface or ice, that probably means there's no friction. There is a normal force because ice is a surface. And there's a force from the rocket. I don't know. I'm going to call it F rocket. You could probably call it F thrust or something like that. I'm going to call it F rocket. Okay, the force from the rocket making it accelerate. Notice, by the way, when you look at my free body diagram, these two forces cancel. F and an Fg cancel. There is a net force. The net force is not equal to 0. Okay, in fact, the net force is to the right, and so the sled is going to accelerate to the right. Now, one last thing before you work on your practice problems. Okay, accelerating to the right and moving to the right are not the same thing. Okay, we talked before about the difference between velocity and acceleration. Okay, velocity tells you which way you're moving. Acceleration tells you which way your velocity is changing. So please don't look at this and say, oh, the rocket's moving to the right. No, you don't know it's moving to the right. The acceleration is to the right. Okay, the acceleration is positive, but remember, going back to the moving man, you can have a negative velocity and a positive acceleration. Okay, all the free body diagram tells you is that the acceleration is to the right. Okay, so net force is not 0. Object is accelerating to the right. Okay, that means that if it's moving to the right, it's speeding up. If it's moving to the left, it's slowing down. Okay, so that's number 1. Number 2, hopefully you can finish the rest of the practice problems on this worksheet. Take a picture and then upload. If you want to try to do it without doing it on scratch paper by going to insert and inserting some arrows, you're welcome to try. I kind of think that will be more difficult. I would definitely recommend you print this out and try to do it on your own, or at least do it on a scratch sheet of paper, take a picture and upload to Canvas. Okay, so as always, please let me know if you have any questions, and I will see you guys in the next video.